Welcome to the deep dive. Our mission, as always, is to take a whole stack of source material articles, specs, you name it, and, well, give you the shortcut to really getting it. Today, we're plunging into network architecture, specifically this pretty big shift in how major service providers handle data routing. We're looking at the old guard, multi-protocol label switching MPLS versus the challenger, segment routing over IPv6 or SRv6.
Yeah, and this isn't just, swapping one box for another. It's more fundamental. We're looking at a real architectural change, moving away from managing these explicit labels, which have their own complexities, towards leveraging pure routing and, well, modern IPv6 addressing.
Okay.
To really grasp what SRv6 brings, you first have to understand the kind of complexity MPLS introduced, especially in these really large multi-domain networks.
Right. And our goal today is to synthesize how SRv6 aims to sort of streamline things, get rid of that multi-domain headache operators have dealt with for a long time.
Exactly.
Okay, so let's unpack that MPLS complexity first. Paint the picture for us. We're talking large networks, right? Not just one single entity.
Definitely not. Think about a big national backbone or a large metro network. It's never just one flat network. It's usually broken up. You'll have multiple core networks, maybe regional zones, call them C1, C2, C3. They're separated by border routers, and each runs its own internal routing protocol, its IGP domain.
So they're administratively separate, running their own show internally?
Precisely. And the big challenge for years has been, how do you get a packet from, say, a device in Core 1 across Core 2 to land in Core 3?
Without spilling all the internal secrets.
Exactly. You don't want Core 1 knowing every single little route inside Core 2. That's bad for security, scalability, administration, all sorts of reasons. And this is where MPLS needed this fairly complex way to stitch these domains together.
And that stitching glue is BGP label unicast, BGPLU. Why was that the specific tool needed here?
Right, BGPLU became essential, because you can't just redistribute all your internal IGP routes across that boundary. That would defeat the purpose of separation. So you set up BGPLU sessions between the border routers, right at those stitching points.
Okay.
And BGPLU does two key things. First, it advertises the basic reachability, hey, I can reach this prefix over here. Second, and this is crucial for MPLS, it carries an explicit label for that prefix.
A label, so it's not just reachability, it's a forwarding instruction.
Exactly. That label tells the next domain how to forward traffic towards that destination without needing to know all the internal hops in the previous domain. It's an abstraction layer.
Okay, BGPLU provides the reachability and the label to cross the border, but doesn't that create its own complexity when the packet is actually moving on the data plane?
Oh, absolutely. This is where you get the infamous label stack. Let's say you have a VPN service, like an L3 VPN, running end-to-end across these domains. Your packet isn't just carrying one label, it's carrying a stack.
A stack. How many labels are we talking?
Typically 3. At the very top, you've got the service label that tells the final router what to do with the VPN traffic. Underneath that, you have the BGPLU label, which is the one that gets you across the domain boundary. And at the bottom, you have the transport label, which handles the hop-by-hop movement within each core domain.
Wow, okay. Service, BGPLU, transport. Managing that stack, especially the context of when each label is valid, that sounds like a nightmare.
It is. It's a significant operational burden. Tracking state, managing label allocation, troubleshooting. It's complex.
And our sources point to one really fundamental constraint that makes it even harder. MPLS needs specific 32 host routes. You can't summarize. Why is that limitation such a big deal?
It's a huge deal because MPLS forwarding fundamentally relies on mapping a label to a unique specific destination prefix, usually the 32 loopback of a router. If you try to summarize, say, 100 32s into one bigger 24 prefix,
You lose the detail.
Right. The label switching router, the LSR, gets the label for the summary, but it doesn't know which specific 32 device inside that summary the traffic is actually for, so it can't apply the correct outgoing label or service instruction. This forces networks to advertise every single 32 host route across the entire infrastructure, which just balloons the routing tables and limits scalability.
Okay, so MPLS is kind of stuck with these 32s and the whole complex BGPLU stitching thing. If that's the main bottleneck, how does SRv6 manage to break free?
That's the pivot point. SRv6 fundamentally changes the game because it's built directly on IPv6. And native IPv6 routing inherently supports prefix summarization. That single fact eliminates the need for BGPLU just for basic reachability and label exchange across domains.
So you still have your separate IGP domains, C1, C2, C3, maybe running ISIS v6 now.
Correct. ISIS version 6 is common.
But instead of needing BGPLU with the borders, you just use standard routing techniques like route summarization between the ISIS v6 domains.
Exactly. Interdomain reachability is achieved simply by injecting summary routes from one domain into the next, using ISIS v6. No complex redistribution gymnastics, no separate BGPLU sessions just for labels. Because we're dealing with IPv6 addresses, we can summarize huge blocks without breaking the underlying forwarding. The result: much cleaner domain boundaries, much smaller routing tables at the borders.
That definitely sounds simpler from a setup perspective. But wait, summarization always has a downside, right? It hides information. What happens if a device, say router X deep inside core 2, goes down? Core 1 still only sees the summary route from core 2, so it thinks router X is up and
Yeah.
keeps sending traffic. That traffic just gets black holed in core 2.
That's the classic problem with summarization. You're absolutely right.
Yeah.
It hides failures within the summarized block. Traffic gets sent towards the summary and then dropped when it hits the point where the specific prefix is actually unreachable. SRv6 anticipates this and has a specific mechanism to deal with it. It's often called unreachable prefix announcement, or UPA, sometimes referred to as area partitioning detection as well.
UPA. Okay, is this just trading one complexity label management for another? A new mechanism to handle exceptions to summarization?
That's a fair point, but I'd argue the nature of the complexity is different and, well, less burdensome. UPA standardizes this exception handling within the existing routing protocol, like ISIS v6 or OSPF v3. You don't need a whole separate protocol like BGPLU with its own state machine and label databases.
How does UPA actually work then?
With UPA, if that specific device, router X, goes down, the area border rail, or the ABR, connecting core 2 to core 1, will explicitly signal, hey, even though I'm advertising this big summary route, just so you know, this specific 128 address within that summary is currently unreachable.
Ah, so it provides an override, a specific notification about the downed device.
Exactly. It allows the source router back in core 1 to know immediately that the specific destination is down, even with the summary in place. It overcomes the main drawback of summarization without needing that whole MPLS label apparatus. It's a routing-based fix.
Interesting. So domains stay separate, but routing becomes more standard, more scalable, with a built-in fix for the summarization issue. Okay, let's get to the core tech then. The segment identifier, the SID, this 128-bit IPv6 address. It's not just an address, it's the instruction itself. That sounds powerful.
It really is. You used the analogy of executable code earlier, and that's not far off. It's like embedding a program directly into the IP header's destination address. The SRv6 SID takes a standard 128-bit IPv6 address and carves it up, giving different parts specific meanings that dictate routing and behavior.
Okay, break down that 128-bit structure for us.
Conceptually, you can think of it in three parts, though the third is often optional in practice. First and most important is the locator. This is the routable part of the SID. Think of it like a subnet assigned specifically for SRv6 functions. It's usually composed of a larger SID block assigned to the network, plus a unique node ID identifying the specific router within that block.
So the locator is basically the network's address for that specific router advertising the segment and tells you where in the network it is.
Precisely. The locator is the part that normal IPv6 routing protocols understand and route towards. It ensures the packet gets efficiently routed to the node that owns that SID using the standard shortest path.
Okay, so the packet follows the locator like a regular IP destination. It arrives at the node. What happens next? It needs instructions, right?
That's where the second part comes in, the function. Once the packet arrives at the node identified by the locator, that node examines the function bits within the SID. The function tells the node what specific action to perform. This is where the segment-aware behavior lives.
What kind of actions?
Oh, things like forward this packet out a specific interface or to a specific neighbor. That's an adjacency SID. Or decapsulate this packet and process it for a specific VPN service, like an L2 VPN or L3 VPN SID. Or even just remove the SRv6 information and process the inner payload.
So locator, where to go in the network, function, what to dig in you get there. Simple enough.
That's the core idea. And then there's the third optional part, the argument. This provides space for more fine-grained details or parameters related to the function. One example is an EVPN, where it might carry an ESI value for filtering traffic in multi-homing scenarios. But honestly, based on the sources and current deployments, the argument isn't heavily used yet. It's often just set to all zeros. So practically speaking, the locator and function are the key mandatory pieces today.
Got it. Locator and function doing the heavy lifting. This address as instruction concept is pretty neat. But let's switch to the data plane, especially for things like traffic engineering. In MPLS, or even SR MPLS, If you want to force traffic down a specific non-shortest path, you stack labels representing the hops. How does SRv6 achieve that without
All right,
labels?
let's quickly recall SRMPLS first. If you wanted a path, say, R1 onto R3, R5, and R6, R1 pushes a stack of labels corresponding to the SIDs for R3, R5, and R6. When the packet gets to R5, the penultimate hop before the final destination, R6.
Penultimate hop popping happens, PHP.
Exactly. R5 pops its label off before sending the packet to R6. This is the implicit null behavior, saves R6 from having to process that last transport label.
Does SRv6 have something similar? An implicit null.
It handles the final hop cleanly, but the mechanism is different because we're not swapping labels. The big challenge for SRv6 source routing is header over head. If you tried to implement a path by just stacking multiple full 128-bit IPv6 headers, one for each explicit hop, well, that would be incredibly inefficient. 40 bytes per hop instruction.
Yeah, your header would quickly become bigger than your payload. Not good for performance. So how does SRv6 list the instructions without that massive overhead?
The solution is the segment routing header, or SRH. And this is critical. It's not another full IPv6 header. It's defined as an IPv6 extension header. The main IPv6 header has that next header field. In SRv6, this field points to the SRH, telling routers, okay, segment routing instructions follow. This is way more efficient than stacking full IP headers.
An extension header. Okay. What's inside the SRH?
The SRH carries two main things: the list of segments, the SIDs representing the explicit path, and a pointer called segments left. This pointer tells the processing router which segment in the list is currently active. Now, here's the slightly quirky but important detail. The segment list in the SRH is processed in reverse order, from bottom to top, effectively.
Reverse order. Why is that? Seems counterintuitive.
It mainly comes down to simplifying how the source node constructs the header. It's easier to push segments onto a list as you build the path, knowing the last one pushed will be the first one processed. Think of it like stacking plates. You take the top one off first.
Okay, reverse order processing. Let's walk through that example. Packet needs to go from A to D, but we want to force it via B and then C.
Right. So A, the source node, builds the packet. It puts the SRH after the main IPv6 header. Inside the SRH, it lists the SIDs for the path, maybe D's final instruction SID, then C's SID, then B's SID. It sets the segment's left pointer to index the last entry in that list, which corresponds to B's SID. Let's say segment's left equals 2, assuming a zero-based index starting from the bottom. Then A copies B's SID, the currently active segment, into the destination address field of the main IPv6 header and sends the packet out.
Ah, okay. So the outer IPv6 header's destination is always the next segment hop. Normal routing just gets the packet to B.
Precisely. The core network just routes based on the destination address it gets to B efficiently. When B receives the packet, it sees its own SID in the destination address. B knows it needs to look at the SRH.
Yeah.
It decrements the segment's left counter. Now it points to C's SID, segment's left at 1.
And ready B.
Then copies the new active segment, which is C's SID, into the main IPv6 destination address field, replacing its own SID. Then it forwards the packet out towards C.
So the destination address keeps getting updated at each segment hop, guided by the SRH list.
Exactly. C receives it, sees its SID in the destination, processes the SRH, decrements segments left. Now it points to D's SID, segments left equals 0. C copies D's SID into the destination address and forwards it. When D receives it, it processes the SRH, sees segments left is 0. This typically signals the end of the SR path. D processes the instruction in its own SID, the function part, maybe decapsulating a VPN, and processes the original payload. The SRH might be removed at this point. It's pure routing steered by that extension header.
That makes sense. It avoids label swapping and leverages standard IP forwarding, just updating the destination based on the SRH list.
Okay, that brings us towards wrapping up. The core takeaway seems to be SRv6 swaps the whole complex world of MPLS label stacks, 32 route dependencies, and BGP-LU stitching. For a model where the intelligence is baked into the IPv6, address itself the SID with its locator and function.
Right. And it simplifies connecting different domains by using standard routing principles like summarization with ISIS v6, plus mechanisms like UPA to handle the known issues with summarization.
It really shifts the paradigm. Instead of relying on intermediate routers constantly swapping labels based on complex state, SRv6 puts more control at the source and embeds the forwarding instructions directly into the packet's addressing and headers.
So, for a final thought to leave our listeners with.
Well, think about this. If a single 128-bit address can now define not only where a packet needs to go, but also what function should be performed when it gets there, What does that imply? What are the broader consequences for network programmability, for security verification, maybe even for troubleshooting when your core forwarding instruction is right there in the address itself, compared to the older model of relying on implicit context and label state distributed throughout the network? That integration of control and data plane into the address, it really changes how you can think about designing and operating networks.
A lot to chew on there. It certainly feels like a more integrated, potentially more powerful approach. This has been a fantastic deep dive, really clarified the core differences. Thanks for walking us through it.
My pleasure. It's a fascinating transition to watch.